Good afternoon, everyone. My name is Dr. Shane Webb. I'm a postdoctoral research fellow at University Laval. I began my postdoc in June of 2024, and it's currently scheduled to expire in June of this year, so I'm in the final few months of my research. In today's presentation, I'll be summarizing my results to date, as well as my plans for the remaining months of my postdoc. Before I start, I want to just apologize if my voice sounds a bit rough. I had some travel difficulties getting here and haven't had much sleep, so apologies for that in advance. Nonetheless, so as I'm sure many of you are pretty familiar with the geological background of the region, my postdoc is based along the Larder Lake Cadillac Break, which is located in the southern Abitibi Greenstone Belt, a region that is highly favorable for gold mineralization given the presence of these major east-west trending structures, colloquially known as breaks. So there are many world-class gold deposits hosted along the Larder Lake Cadillac Break, for example, Canadian Malarctic, Kerr Addison, the Kirkland Lake Gold Deposit. While Shafak has worked along the Porcupine Destor Fault Zone, my research is a very similar project, although it's just occurring along the adjacent structure, the Larder Lake Cadillac Break, where there are similarly many of these outstanding issues regarding the uncertainties of the genesis of the gold mineralization, and that's ultimately the research gap that my own project has attempted to fill. So in terms of the research aims that I've been undertaking at Laval, there are essentially three different prongs to my research. The first is I've been attempting to constrain the age of gold mineralization by using in situ uranium-led geochronology, targeting phosphatic phases such as monazites and xenotimes. Secondly, I've been trying to assess the sources of sulfur and the physicochemical conditions associated with the gold mineralization, mainly through the use of sulfur isotopes, including a series of in situ sulfur isotope analyses that are currently ongoing at the University of Alberta. And finally, we've been trying to evaluate fluid transportation pathways and the nature of the fluids associated with the mineralization through the combined use of oxygen and hydrogen isotopes. So our aim is to synthesize these disparate data sets into an overall interpretation of the regional gold metallogenic processes that have occurred along a part of the Larder Lake Cadillac Break. So on this map, you can see this area is broadly speaking where I have sampled throughout the region. So I've sampled approximately 60 localities, although I should stress that most of those localities are simply being used for the regional isotopic analyses, things like Delta 34 sulfur analyses on bulk pyrite samples, oxygen isotope analyses on quartz. So for example, I visited Shining Tree as part of my Young-Davidson visit in May of 2025, but I've decided not to focus any of the in situ sulfur or geochronological analyses on the prospects down there, mainly because I want to keep a clear and consistent narrative and focus my project along the Larder Lake Cadillac Break. So I've sampled a variety of different prospects. I've gone underground sampling at Macassa and Young-Davidson. I've sampled core from several of the exploration projects in the region, for example, the Gatling projects adjacent to Kerr Addison. And then I've largely sampled outcrops of vein-hosted mineralization on the surface, including many abandoned or poorly known claims that are just listed in the OGS database as being gold-bearing veins. I should note that I've also collected a series of high-grade gold samples from the historic gold mines around Kirkland Lake, so I have access to those samples in addition to the underground sampling that I did myself at Macassa. Now, as a result of my own fieldwork throughout the region, as well as my synthesis of the pre-existing literature, I've conceptualized a broad overarching scheme to divide the different deposits that occur in the region. So, for example, along the Larder Lake Cadillac Break, you can find these cyanite-hosted gold deposits. Examples would include Macassa, the South Mine Complex, Young-Davidson, or even Upper Beaver. So this is pretty self-explanatory. These deposits are hosted in the cyanite, and in terms of their mineralogy, in addition to having pyrite and gold, they'll contain large quantities of base metals, such as molybdenite and chalcopyrite. The other deposit style that I recognize are what I term classical orogenic gold deposits. So these are structurally controlled, mineralogically simple quartz carbonate pyrite veins that cross-cut the ultramafics or the Temiskaming metasediments. They are often a bit younger than the cyanide-hosted gold deposits, having formed during the D stages associated with the orogenic events after 2660 MA, I believe. And examples of these deposits include things like the Gatling properties like Cheminus or Anoki McBean. So once I collected all of these samples, I generally made at least one thin section from every locality that I sampled, and I undertook extensive petrographic characterization. Now, the aims or purposes rather of my petrographic characterization were twofold. The first thing I wanted to do was to identify large quantities of phosphatic phases, xenotimes and monazites for EPMA analysis and subsequent in situ uranium-lead geochronology. And where possible, I tried to target my analyses on the phosphatic phases that were associated with the sulfide mineralization and the gold mineralization, although in some cases we've analyzed phosphatic phases that may occur within the alteration zones, like what Shafak showed, or even floating within the quartz carbonate matrix. The other purpose of the petrographic characterization was to provide added context for the ongoing in situ sulfur isotope analyses at the University of Alberta. So I wanted to get a good sense of the different types of pyrite that you find within each of the gold deposits and their relative paragenesis to one another. So, for example, several of the deposits will often contain a euhedral generation of pyrite that doesn't really contain gold, whilst others may contain later pyrite that is more anhedral, fine-grained, and associated with the gold mineralization. So having this sort of context has been important when I've selected my regions of interest for the ongoing in situ sulfur isotope analyses at the University of Alberta. Now, I mentioned that with most of the localities that I've been to, I've largely just done regional isotopic analyses. I haven't dated everything. I haven't attempted to do in situ sulfur isotope analyses on every deposit. And I just wanted to include this slide to provide some context as to why I chose to date what I did and why I coupled the sulfur isotope analyses to those samples. So it's often simply the constraints of nature. Most of the deposits or rather the prospects that I sampled don't really contain large quantities of datable minerals, and they don't really contain large quantities of datable minerals bigger than 10 microns, which is what we really need to date. Fortuitously low, it tends to be the deposits of interest, either the historic mines, the active mines, or the exploration projects where we can find large quantities of datable minerals. I don't actually know why that is, but it's very fortunate anyway. So when it comes to the deposits of interest, by deposit of interest, I generally mean a locality where I've attempted to do both in situ uranium-lead geochronology and then attempted to couple that sample with in situ sulfur isotope analyses. So I've generally wanted to do both of these major kinds of analyses on the same samples or same deposits, so I have as much context, or rather can interpret the data in a more powerful and meaningful way. So generally speaking, we have about less than 10 deposits located along the break where I've done these analyses, and they cover a pretty large area and also are hosted in both cyanites and then the general, the category of orogenic gold mineralization that I described previously. So with regards to geochronology, like Shafak, I had some difficulty dating the monazites, and I've included this to show you a really bad example of what the monazite data can actually look like. So I first went to the University of New Brunswick in October to date the monazites. And the reason why I chose to really focus on dating monazites in that visit is because I had a lot more monazites than xenotimes. The monazites were often a lot bigger than the xenotimes, and therefore somewhat of an easier practice data set for me to learn how to conduct these analyses myself. So I went to New Brunswick. I focused on dating the monazites initially, and many of the samples, they just didn't yield good ages. So, for example, in this case, they are a bit older than the host rocks themselves. With Mikasa and Young-Davidson, I dated hundreds of monazites, I believe, because I simply couldn't find any xenotimes in those deposits, and whenever it's a deposit of such such commercial importance, like Macassa or Young-Davidson, I've really wanted to try to derive an age. And even though I analysed hundreds, there are only maybe tens of the samples that will actually give a concordant age. Now, the age that I actually got for Macassa and Young-Davidson, it was broadly speaking quite similar. These monazites tended to be 2670 plus or minus 10 MA. Interestingly, in the context of Macassa, that age is actually somewhat similar to the very limited rhenium-osmium dating that has been done on molybdenite at that deposit. So Ispolatov et al. 2008, they reported an age of 2675 plus or minus 6 MA from Macassa, and in some ways it's not surprising because during the petrographic characterization, the monazite does tend to be quite closely associated with the molybdenite at Macassa. So I actually went to New Brunswick last week to date the xenotimes. And as you can imagine, I'm still working through that data, and as soon as I return to Laval next week, I plan to try to process that data. So I really have, I've analysed large quantities of xenotime from Cheminis, from Inoki McBean, Fernland, Kerr Addison, but I've also analysed some xenotimes from the Wildcat zone of Wasamac and also one of the Lac Fortune veins as well. So some of the preliminary work that I managed to get done on the xenotimes in October, they were yielding an age of 2643 plus or minus 7 MA, which is unsurprisingly a bit younger than the cyanide-hosted style of mineralization. So moving on to describing the other types of analyses that we've done. So Shafak and I, in order to provide as much context for our in situ sulfur isotope data set, we did some trace element mapping of the different pyrite generations that we're targeting. And one of the interesting things that I observed when we did this, at least for the orogenic style prospects, we do often see quite clear oscillatory zonation in the trace element geochem. So it's often the case that the cores of the crystals will contain elevated concentrations of cobalt and nickel, whereas the rim will have a large quantity of bismuth, tellurium, lead, gold, antimony. I think similar textural relationships were described from the orogenic prospects around Val d'Or by Herzog et al. Interpreting the trace element geochem data from the cyanide-hosted mineralization has been a bit more challenging because it's often the case that the trace elements, regardless of what they are concentrated in particular fractures or domains. I think that this might be the result of extensive remobilization processes that seem to characterize a lot of the pyrite within the cyanide-hosted gold deposits. So regardless, having this information regarding the pyrites is pretty important because it gives us an extra context to interpret the spots that we'll eventually get from the in situ sulfur isotope analyses. So it will help us to interpret the variation from core to rim. So moving on to the sulfur isotope study. So I mentioned that at the minute, our in situ sulfur isotope analyses are currently ongoing at the University of Alberta. However, we've completed our bulk delta 34 sulfur isotope analyses, and by that I mean analyses where we've gotten a Dremel, we've drilled the pyrite out, and we've sent it away to a lab in Ottawa to analyze the delta 34 sulfur signature. Now, this data is naturally a bit limited because you don't have a petrographic context in which to interpret it, and furthermore, the delta 34 sulfur ratio is often the result of a complex interplay between physicochemical factors such as temperature, pH, oxygen fugacity. It's not simply controlled by the source of the sulfur. Nonetheless, having this kind of data as a preliminary data set prior to doing the in situ sulfur isotope studies is pretty important for seeing what regional trends may occur along the Larder Lake Cadillac break. So I analyzed about 60 pyrite samples from the different projects, or prospects rather, and generally speaking, what we see is values that are very typical of Archean orogenic gold systems, values of between 0 plus or minus 5 per mil. However, the Kirkland Lake gold deposit appears to represent a bit of a regional anomaly because it contains very depleted delta 34 sulfur values that are as low as minus 16, minus 17 per mil. Now, as I mentioned, using the bulk delta 34 sulfur isotope value by itself is somewhat limited because of all of the factors that can control it. So based on this data set alone, it's very difficult to speculate on what the actual causes of that depletion might be. My hope is that when we complete the in situ sulfur isotope analyses on the Kirkland Lake gold deposit, because we'll be using multiple sulfur isotopes like 32S, 33S, we'll get a much better handle on what the drivers of this variation actually are. And just to show you what I mean by this, so I've prepared regions of interest, not just from Macassa, where I've also done geochronology, but I've prepared regions of interest from the historical Kirkland Lake gold mines that traverse the ore body. So again, like I said, I hope that the in situ sulfur isotope analyses can help us assess whether the source of sulfur varies within the deposit and what the actual causes of this depletion actually are. So as Shafak mentioned, oxygen isotope analyses are a pretty important aspect of our research, and to date I'm in the same position as him where I finished doing my oxygen isotope analyses on the quartz. So I've largely analysed about 130, 140 quartz samples between Rowan Naranda and Shining Tree. But on this slide I'm just summarising the work that has been done to date by the Metal Earth team and others. So it's generally the case that the fluid delta 18O value that they have obtained from this region is normally between +9 and +13 per mil, which even though some mixing has been invoked, it's very typical of metamorphic fluids in this region. With my own data set, I see largely quite similar values, except again, the South Mine complex of the Kirkland Lake gold deposit shows a pretty depleted signature in some cases of +4 to +5 per mil. So it's we are again seeing this overall trend where the Kirkland Lake gold deposit seems to defy regional trends in the isotope systems. We've also conducted delta hydrogen analyses on tourmalines and phyllosilicates such as chlorite and sericite. So to date, we've completed about 50 of these analyses. The values, again, they're pretty typical to what Cannell et al. 2023 document for orogenic systems in the Abitibi belt. And in particular, the tourmaline values that I have, they're quite similar to what was described from the tourmaline-bearing veins around Val d'Or. The real aim with this data, however, is to eventually create a diagram like this. So as Shafak mentioned, when we go back to Laval, we are now running oxygen isotope analyses on these tourmalines and on these phyllosilicates. I have about 4 more runs to do before I will finish this, and then we can attempt to construct this diagram, which can be used to try and fingerprint the actual source, the potential source of the ore-forming fluids with a greater level of accuracy. Similarly, if we have the oxygen isotope value of the quartz and the oxygen isotope value of the tourmaline or phyllosilicate pair, we can use that to estimate the temperature more accurately. So just to summarize, in terms of the implications for the regional metallogeny, it appears to be the case that I can recognize these 2 distinct styles along the region. We have these cyanide-hosted gold deposits, which appear to be slightly older, and then slightly younger orogenic style gold deposits. And in several instances, this temporal difference appears to map on to a contrast in the isotopic signature of the fluids, the geochemistry of the deposits, and also even the mineral assemblages. I should note, however, that the deposit styles are not actually spatially exclusive, and there are numerous occurrences where these cyanide-hosted deposits have been overprinted by what appear to be orogenic veins. So I think this might have already been described in the literature at Upper Beaver, where you have the intrusion-related deposit that has then been overprinted by quartz carbonate tourmaline veins. And then for example, at Young-Davidson, I found this suite of quartz carbonate tourmaline veins that appear to cross-cut everything, and you can't really interpret them within the pre-existing vein framework that has been published for the mine already. So I think that this is in some ways not surprising, because the cyanites are probably likely to form a pretty favorable host for later mineralizing fluids given their competency. So again, you may see these overprinting relationships. So just to conclude, when I return to Laval, I basically have 3 priorities that I need to do immediately. I need to process all of the geochron data that I've just collected from New Brunswick, particularly on the xenotimes, so I can better validate my preliminary interpretations regarding the timing of these cyanide-hosted versus orogenic gold prospects. Secondly, I need to finish running the tourmalines and the phyllosilicate samples on the line As I mentioned, I ran the first tourmaline session this week actually, and we only have about 4 more to do before that will be finished. And then finally, I need to make sure that the ongoing in situ sulfur isotope analyses at Alberta are completed within the coming weeks and months. So I should also note that based on my experience at the Metal Earth Conference, I've actually learned some very important things that I will need to feed in and incorporate to my approach as I continue to process and synthesize the data. Thank you for your time. I'm happy to take questions.